Hi, this is the fourth in the series of benzene videos. I thought I'd deal with terminology, so some words I need to explain, and then get on to uses of nitrobenzene type compounds. So let's get started. When I spoke to you earlier on previous videos, I called the carboxylic acid that is there, that carboxylic acid, I called it benzoic acid. Now benzoic acid is the common name, and we shouldn't really use the common name when there is a more modern, a UPAC nomenclature name, which is benzene carboxylic acid. Benzene carboxylic acid. Now, as you can see from that, I called it benzoic acid. The proper name is benzene carboxylic acid, and that's a function of me being old. I think it will happen that as an old teacher I will use old terminology and old words to describe modern things because I haven't moved on. I'm stuck in the past, and things like that will happen. I still spell sulfur with a PH when now the modern young thrusting chemists, teachers spell it with an F. I apologise for that, but I suppose I will make more of these errors as I go along, and I would say to you that you should take the lead from your young teachers or new textbooks or the MGS booklets that we have to just double check the things like this are correct in your mind, and will guard you for the future rather than put you in the past. So what else do I need to talk to you about? Well, I suppose I'd like to talk next about the words aliphatic and aromatic. Now this is in organic chemistry. When we have normal organic chemistry and we've got normal straight chain molecules like propane, butane, they're all in a straight chain and we call them aliphatic. Equally, we might have some rings like cyclohexane or cyclobutane, cyclopropane, and equally they're aliphatic because they're just normal compounds in a ring structure. But as we saw last time when we dealt with benzene, there is the prospect of having alternate double single bonds. Now where we have double single bonds, then we can get this delocalization of electrons that I spoke about last time, and that delocalization of electrons will change the behavior of the molecule if it's present. So we have a different word for where that delocalization occurs, and that delocalization of electrons changing the properties of compounds, and the word we're going to use from now on is aromatic. Now because within A level the aromatic compounds are of benzene, then basically for A level what you need to learn is that aromatic compounds involve benzene rings, whereas aliphatic compounds do not involve benzene rings. So when we're talking about, for example, bromobutane would be aliphatic. because it's not got any benzene rings. Whereas we're talking about bromobenzene, bromobenzene would be aromatic. So I want you to use the terms correctly: aliphatic and aromatic. And basically at A level, just benzene rings. In a wider sense, the word aromatic can be used for any system where you've got double, single bonds, this delocalization of electrons taking place. And there are other ring structures where this happens too, not just benzene. But for A level, it will just involve benzene. Other words is, if we're talking about those kind of structures, let's talk about the idea of conjugation. Conjugation. Now, we learnt in a previous lesson that you can draw benzene as a kekulé structure. Structure is not that, but if you have C6H6, you can draw it like that, or you can put the double bonds in the other positions, like there, there, and there. And what some people think about is that the benzene structure flips between the two structures, it oscillates between the two, and these words I'm using, like flips and oscillates, are not right. There is a word that describes this rapidly interchanging between two structures like this, and the word in chemistry is resonance. Now you can show resonance quite easily by saying that what if the two electrons there move there, and then the two there move there, and then the two there move there? That would turn structure 1 into structure 2. But what would have to happen to 2? Well, in 2, the flipping of electrons, the 6 electrons, to new positions could take place to regenerate for U1. Where we've got this happening, we call it resonance. Now in benzene, this happens because we've got alternate double single bonds, and we show it overall as with a little ring inside to show the delocalization of electrons that occurs. So that, where my pen is pointing, that is what I want you to draw for benzene. However, books sometimes talk about this kekulé structure, they talk about resonance, and overall everybody's agreed that real benzene has a lower energy than these kekulé structures. It's got lower energy, it's more stable, and it was more stable by 152 kilojoules per mole more stable. And when it has this extra stability, then this quantity of energy is known as either a resonance energy or delocalization energy. So to show the extra stability of benzene, you can use the phrases. You can use the phrases resonance energy or delocalization energy. What other terminology do I want to deal with? Well, I think I want to deal with nitrating next, to lead us on to reactions of where we're making nitro compounds. And basically, to do nitration reactions, you need the electrophile, which I explained to you, NO2+, and we generate that electrophile by mixing nitric and sulfuric acids together, but I'll talk about that in a minute. But this electrophile, I didn't name it. And perhaps you should be aware of the name of this. The name of it is nitronium. Nitronium ion. So it's generated with using 50% conc nitric and 50% conc sulfuric. Generates for you this nitronium ion, which is the electrophile, which will do nitration reactions for you. Carrying on for that, perhaps part of the same idea, is the mixture. The mixture of having conc nitric acid and having conc sulfuric acid together as a mixture in a 1-to-1 ratio is known as, believe it or not, it's known as the nitrating mixture. Now this nitrating mixture is famous for making explosives. When you have this nitrating mixture, you should exercise caution, you keep it cold, particularly if you're doing nitration reactions. You may well be making explosives, which I'm going to show you in a minute, one such reaction. And when you do so, the temperature is kept below 50 degrees Celsius. The cold temperature stops detonation of your explosive that you're trying to make. Just generally, when we're making explosives, you should keep the reaction cold and you should keep the reaction wet. A lot of explosives will detonate when they're dry and when there's a spark or warmed up in some way. So then I can go on to talk about the reactions of benzene, and we talked about nitration. I want to go back and revisit that. Nitration. And what we learned was that already we learned that benzene with nitric acid will make, with sulfuric acid catalyst, will make for you nitrobenzene. And water. Now, I went through the reaction in more detail in a previous video, but what I want to talk to you now is, what if we do this not with benzene, but what if we start with methyl benzene? So CH3 methyl group attached to benzene. Methyl benzene is the modern name, the UPAC name, but I'm going to call it toluene, because toluene is the common name, the old name, the common name. And what if we were to react that with nitric acid in the presence of sulfuric acid, both concentrated, catalyst? Then you might think, yes, we're going to get nitration in the same way that we've got nitration up there, and you would be right. We do get nitration. However, we don't just get one nitration. When we carry this out, the substitution of the nitronium ion happens not just at one position, but it happens at that position and the nitro group substitutes. It happens at that position and the nitro group substitutes, and it happens at that position and the nitro group substitutes. So what do we call this? Well, the nitro groups are at the 2, 4, 6 positions. You could call it 2, 4, 6 hyphen tri nitro methyl benzene, but I want to call it trinitro toluene. Now the reason I want to do that is The reason I want to do that is I want to call it TNT. And that is a famous explosive. Now we need to just balance all this up. You need 3 of those. And when you do that, you're going to get kicked out waters. How much waters? You're going to get kicked out 3 H2O. Nitro groups, 3 of them, each one gives an O. Right, okay, I think that's balanced. So TNT, famous explosive. And that's just how I want to just give you an example where we keep the temperature below 50 degrees for safety reasons. We do the reaction with the nitrating mixture, and the nitrating mixture makes for you trinitrotoluene, which is TNT, or 2,4,6 trinitromethylbenzene, if you want the correct name. So one use of nitro compounds is as explosives. So nitro compounds as explosives. However, I want to talk to you about another use. And this is really quite an important use. It's starting with nitrobenzene and making phenylamine. Making phenylamine. Phenylamine. Now, nitrobenzene is NO2 with benzene. Phenylamine is an amine, it's NH2. NH2 with benzene. And to turn one of these, nitrobenzene, into phenylamine, then clearly you have to do something called a reduction. This has to lose oxygen and it has to gain hydrogen in order to turn it into the phenylamine. And therefore it's clearly a reduction. How do we do it? Well, there are 2 ways to do this. You can either use something you've come across before, hydrogen gas with nickel catalyst. And if you go into transition metal chemistry, we will explain how nickel catalyst works in this hydrogenation reaction. But you can do reduction, like the addition of hydrogen is reduction. You can do reduction using hydrogen gas and nickel catalyst. Now, when we in schools try and do this, hydrogen gas is not easy to handle in schools by pupils, and we tend not to do it this way. There's another way. And equally, industry tends not to do it this way. They tend to do it a different way. And the different way is B. Now, this other way, I'm going to use tin. Tin and hydrochloric acid. Now, if I were to say to you that your famous oxidizing agents are acidified dichromate or acidified manganetes, then hopefully you'd remember that from the past. Well, what famous reducing mixtures do you have? Well, I want you to learn equally, and you're going to need this in transition metal chemistry, that the reducing mixtures are tin with hydrochloric acid, or indeed you can use zinc with hydrochloric acid. The idea is that the hydrochloric acid will react with a metal, and the metal turns into ions. So zinc turns into 2+ ions, tin turns into 4+ ions. Either of those reactions is clearly an oxidation. The oxidation number is increasing of the metal. And as the metal is oxidized, then something else, somewhere, must be being reduced. And that's how the reducing action actually happens. So, if we use this mixture, how do we show it in an equation? Well, the easiest way to show it in an equation is similar to if we were using acidified dichromate, acidified manganate, when we were showing those as oxidizers we used O in square brackets to simplify the equation. Well, we use a similar thing here. For reduction, we're going to show H in square brackets. So if we write H in square brackets there, and we turn that into NO2, not NO2, we're turning into phenylamine. So we turn that into NH2, the benzene ring goes unchanged, and we need we need 6 of them to balance it up, because 2 go there, the 2 oxygens that fall off are going to make 2 lots of water. So that is how we show that reduction of tin and hydrochloric acid. And if we do this in school, we use tin and hydrochloric acid. Easy to do, test tube type reactions. You get hydrochloric acid, you throw in there granules of tin or granules of zinc, and you if you're worried about reoxidation, you just put a layer of glycerol over the top to stop air getting in. Alternatively, if you're not worried about reoxidation, then you just leave it, you leave the reduction to happen, and this reaction will happen nicely, making for you phenylamine. Now, phenylamine is so very useful in our world. You might ask, what uses? Well, phenylamine, that's a new UPAC name, is aniline. And aniline in our world is used for some great uses. The main one is to make diazo dyes. Now, that diazo dyes and other diazo compounds, which are quite often present, diazo compounds are present in manufacture of drugs. Dyes and drugs, I would say to you, are really valuable. Starter material is aniline or phenylamine. Other uses of phenylamine, let's just write them down. So, this is used, phenylamine is used to make diazo compounds. Now, diazo compounds are compounds that have that structure within them, diazo compounds. Quite often you've got benzene rings on this side and benzene rings on that side. These are used to make these diazo compounds, and the diazo compounds themselves are great for dyes, drugs, and other things. But what are the uses of aniline? Well, the other uses are to make rubbers or to make pesticides. Now, rubbers like tires and balloons, you need aniline in their manufacture, and you can use aniline as pesticides in making pesticides. However, in an exam, if they ask you, I want you to focus on use to make diazo compounds. I think this diazo compound manufacture is much more useful than rubbers and pesticides. I mean, clearly rubbers and pesticides are important in our world, but I think that this variety that you get from diazo compounds is, in my opinion at least, even more important. So there you have the uses of nitro compounds. Okay, so if this video turns out okay, I'm going to try video 5, next one, and I'm going to try and deliver that on Friedel craft reactions. Now they're interesting, they're really interesting. Well, I find them interesting. I hope you will find them interesting. Join me on the next video.